so let's see. What we're going to be looking at is, in this particular section, in 7.3, you're looking at trigonometric integrals, and we're going to kind of look for a little bit on powers, like some trig function to a power. Like this one's the cosine fifth power of x. And there's different strategies you have to use. There's a couple of things that I wanted to mention on here that are kind of important with these, and one thing that's probably worth writing down on here is these three identities, and you want to make sure you know these three identities, okay? And I'm going to go through how I derive those, because that's the one I remember, and everybody remembers that one. The other two I don't remember. I derive them as I write them down. So let me kind of explain how I do this. If I divide everything by cosine squared of x, okay, what is the sine over the cosine?
Tangent.
That's a tangent. I'm trying to show you how I do this in my head. Okay, what's a cosine divided by a cosine? 1. What's 1 over cosine? Okay, see, that's how I do that. I never remember it. I just derive it as I go, and those are good things to learn how to do. Now I divide everything by the sine. Okay, so sine squared divided by sine squared is 1. Cosine squared divided by sine squared is cotangent squared. And then 1 divided by sine squared is cosecant squared. You guys see what I'm doing or not? I mean, memorize them. But to me, the less you memorize and the more you derive and figure out, the better off you are. So when you're dealing with this section, those things are going to come in handy. And then these identities right here, I think I've already got these written down on your handout. This one did have a typo on it, so that should say sine squared x is 1 minus cosine 2x over 2. These are the half angle identities, which we've looked at before. You're going to use these pretty extensively in this section, okay? Okay, so here's the idea. We're going to look at different strategies. So if you have like an odd power, we're going to focus on odd powers, you usually split this into an even power and one left over. So what I'm going to have you do to start with is we're going to write this as the integral of cosine to the fourth of x times the cosine of x dx, like that. So you want to start off like that. And the reason you do that, ultimately, when you're doing an integral of a cosine, you would like there to be a sine in there too for U-substitution, right? Sine and cosine needs to be there, okay? So what we're going to do is we're going to take advantage of this identity when we do this. So I'm going to actually have you write this now like this. We're going to write this as cosine squared of x, and then the whole thing squared like that, okay? So what I'm trying to do is I'm trying to break that down into a cosine squared so I can apply this identity, see? Okay? Then once I do that, then we'll see if we have something that we can do on that one then. Okay? Now what I'm going to do here, before I do that identity, and actually I'm going to use this, we're going to go ahead and I'm going to write this like this, okay? I'm going to change this cosine to 1 minus sine squared x, then the whole thing squared, and then we have cosine x dx like that, okay? Actually, I'm not going to use the half angle identity on that. We do a lot of times, but the approach on this one is to try to introduce a sign in there, okay? Now, see, that's part of the challenge on there is you want to have a sine and a cosine, so we've got that. Okay, you guys following me so far? Okay? Now, U-substitution works very well from here, so let's kind of think about what we would do with U-substitution. Okay, what would be a good thing to set U equal to in this problem? Yeah, not just the sign, but the whole thing. Okay. Oh, no, the sign would be good. You're right. I'm thinking wrong there. So let's just work it with the sign. Okay, like that. So that thing right there is going to be U, and then you're going to square it. And then, of course, we would have du is equal to the cosine of x dx like that. Okay? So let's see what we have with the U-substitution now. So the thing, of course, right here is going to be the du. So let's see if we got an integral that we can handle now. So this is going to end up being the integral of 1 minus u squared to the second times du like that. Okay, now I think we can handle that integral. How would you go about doing that integral probably? Just multiply it out, right? Multiply it out and then it's power rule. So this one turns out to be pretty nice, okay? So what I'm going to go ahead and do is we're going to square this now, and hopefully you guys can square this in your head. 1 to the second's 1. Then you multiply 1 times u to get negative u to the second. Then you got to double that like that. Then you square the last term. You're going to have plus u to the fourth like that times du. Okay? Write it out twice and FOIL it if you need to. Okay? All right, now we integrate. Okay, so what's the integral of 1? U. Then we have 2u to the third over 3. Then we have u to the fifth over 5 plus c like that. Now all we got to do to conclude the problem now is just plug back in our u. So u was sine x. So everywhere I see a u, I just plug it back in. So my final answer on this looks like it would be sine of x minus 2 sine cubed of x over 3, and then plus sine to the fifth of x over 5 like that. So you could write it like that, okay? Or you can write that as a 2/3 and a 1/5 if you want to, like that. Okay, that's probably the simplest problem I teach in the whole section. I get harder from here. So how's that look? Okay, these things get pretty messy, so get ready. Okay, and it's the next section that kind of gets that way too. All right, is there any question? You guys follow what I did on that? So as you're learning how to do these things, you want to kind of keep track of the strategies. That's generally how you deal with an odd power of just a sine or a cosine. Split it up into an even and one left over. And then you generally use one of these Pythagorean identities when you do that, okay? Okay, now let's see what we got on this one now. Now we're going to look at kind of an even power. And when you work with an even power, you take a different approach on it. So generally what you do is when you have an even power, you end up using these half-angle formulas, okay? Again, this is a typo. That should be, you might want to write that in there. That's cosine 2x. So we've already looked at those identities, so we're going to use them a lot when we have sine squared or cosine squared, okay? So what I'm going to do on this one is let's start off by writing this out as sine squared of x all to the second times dx like that. Now you wouldn't want to use the Pythagorean identity because if you change that to 1 minus cosine squared, that accomplishes nothing. You wouldn't be able to do it with U-substitution. So what we're going to do here is we're going to replace this with this, and then we're going to see if we can go through and integrate that then. Okay, so let's go ahead and do that. So in our next step, we're going to write this as, replace that with 1 minus cosine of 2x all over 2 squared times dx like that. Okay, now what you're going to need to do is multiply that out. U-substitution wouldn't do anything. Integration by parts would be a disaster, so we just have to multiply it out and see where that takes us. Okay, all right. Well, let's see. If you want to, let's go ahead and write this out twice. You can do this in your head too if you're squaring. I think I'll just probably see it a little better if we just multiply it out twice and then think about how the FOIL would go on this. Okay, so I'm going to go ahead and do that, and then we'll kind of see what we're left with. All right, so what we want to do on this, first of all, notice that you'd have 2 times 2, that's 4. That's a constant. So what I would do is I would bring that 1/4 out of the integral, and then I would just multiply out this, this numerator here. Okay, so you can just FOIL that out, and you can do that in your head if you want to. So if you do that, you'd have 1 minus 2 cosine 2x plus cosine squared of 2x dx like that. Okay, and I just did the FOIL in my head on that. That's kind of like squaring, like we've learned how to square anyway. Okay, so now when you look at this thing for a little bit, let me kind of show you something on this and see what your thought process is. Okay, well, you know how to integrate that, right? Obviously. Do you know how to integrate that? We've learned that. That's a formula. Okay, how about this? Right there. Okay, you got to use that identity again to do that. Because see, if you have like cosine of AX, you can integrate that. This thing you can't integrate until you apply that again. So we actually have to go through and plug that identity in one more time. Okay, so as you're going through this, kind of think, okay, am I ready to integrate or do I have anything else to do? So what I'm going to do is bring this down. I'm just going to try to get everything set up before I integrate. So I'm going to have 1 minus 2 cosine 2x. Okay, now what I'm going to do is I'm going to replace the cosine squared with this. And watch carefully how I do this. You don't want to slip up on this now. So what I'm going to do is we're going to replace this with this. So it's going to be 1 plus cosine, but it's not going to be 2x. What is it going to be? 4x. Good. See, what you're always doing in this half angle identity, this thing is always double what that is. So you have to double that 2x and you have to make that a 4x like that all over 2. Now you're getting down to a point where you can integrate. Okay, see that thing right there, this argument can be anything, but that thing right there is always going to be double that. Okay, does everybody see that? Okay, don't slip up on that. That's real super important when you're doing that. Okay, so now we're getting pretty close. So what I'm going to do on this now is just kind of break it up like this. I'm going to write one more step before we integrate it. So we got the 1/4. We got the integral of 1 minus 2 cosine 2x. And then this thing right here, we could write that kind of like this, split it up. Okay, write that as 1/2. And then you could write this as 1/2 cosine of 4x. The whole thing times dx like that. Now what you can do is you can integrate everything on this if you look at this, okay? All right, so are you guys following where I'm at so far? Okay, all right, I like to write lots of steps so I don't mess up on anything. So one of the things I'm going to do, I'm going to write one more integral step. You could bypass it if you want to and start integrating. I see a like term, so I'm going to go ahead and put it together. So like 1 plus 1/2 is like 3/2, so I'm going to go ahead and put that together. So that's going to be 3/2, and then minus 2 cosine 2x, and plus 1/2 cosine 4x dx. It's good to write lots of steps. Even if you got 20 steps, write 20 steps. Just do it very methodically, one grouping at a time. All right, I'm ready to integrate now. Okay, so now you get to a point now, if you know your integral rule, then you're in business. So one of the things we learned, like if you had the integral of cosine ax, what was that? 1 over a sine of ax, right? Okay, plus c. Okay, because you got that 1 over a there that you have to work with. So you're going to bring down the 1/4. Okay, the integral of 3/2 is 3/2 x. That's easy. This one you would bring down the 2. And then when you do the integral of cosine of 2x, that's 1 over 2 sine of 2x. Okay, that takes care of that one. Okay, then you bring down the 1/2. The integral of cosine of 4x is what? 1 over 4 sine 4x, like that, plus c. Okay, now we just got to clean it up and kind of see where that leaves us then. So what I'm going to do with this is I'm going to write a couple of more steps and then we'll have the final answer. So I'm going to just bring everything down, doing some easy things like you can cross out the 2's, and that would be sine 2x. Okay, this looks like that would be 1/8 when you multiply that out. Okay, and then finally what I'm going to choose to do is just go ahead and just do like a distributive property on that. Okay, so if I do the distributive property, then I should have a valid answer. So I'm doing 1/4 times 3/2 is 3/8 x. 1/4 times the sine is 1/4 sine 2x. Okay, then 1/4 times 1/8 is 1 over 32 sine of 4x plus c. There be your answer. Okay, a lot of work. That one still to me is not too bad. Okay, because but the thing is, you got to be very methodical and know how to use those half-angle identities. Okay, all right, then you could differentiate it and check it if you wanted to after all that work. Okay, all right, you guys follow what I did? Okay, so remember, you got to pay attention to the strategies on these things. What I'm kind of showing you on this one is, this is the general strategy if you have a trig function to an even power. We're mostly focusing on sine and cosine to an even power. So you leave it alone and then you use those identities. Okay, that's the idea. And you will take advantage of that thing. Okay, and the identities. What's that?
Can you explain how you got 4x again?
Yes, okay. That's kind of a key thing on there. See, the idea is, just as an example, if you had something like cosine squared of 10x, when you're looking at this identity, that's the same as 1 plus cosine, and what does it say? Double that, whatever that is. So double 10 would be 20x over 2 like that. So if you had cosine squared of 10x, that's what it would be. Does that make sense? Because see, that's what it says. It says double the angle. That whatever that angle is, you start with, double it. So that's how I got the 4x. Okay? All right, very good. Okay, now let's go to this one. And this one is pretty heavy. These things get a little get messy. This one you may have to write small on your paper, because I've got like about 20 steps on this one, I think. So watch carefully. Now, what you want to kind of do with this one is, you've got two trig functions. You have a sine and cosine. So when I think about doing an integral of the sine and cosine, I like having a sine and cosine in the integral, because that kind of makes me think of a good U-substitution. Okay? But one of the things you got to do on this one is you have even powers, so you got to take advantage of those half-angle formulas. So let me just write down these for reference. You can write them down if you want to. Sine of 2x is 1 minus, whoops, I'm writing that wrong. I mean sine squared of x, not sine of 2x. So we have sine squared of x is equal to 1 minus sine of 2x, or cosine of 2x, rather. Over 2, and then the other one we have is the cosine squared of x. It's the same thing, except it's got a plus sign. So that's 1 plus cosine of 2x over 2. Okay? So you want to make sure that you know those identities and you're able to apply them. So if it's got an even power, that's generally what you do. That's the general idea, is just think about using those identities. So the way I'm going to approach this one at the beginning here is I'm going to write this as, I'm going to go ahead and write this as sine squared of x to the second, and then just leave the cosine squared of x alone like that. Okay? So we're going to kind of see what we can do there. Now what I'm going to do is I'm going to do the half angle identity. So I'm going to look at the sine squared of x. We're going to replace it with that. And then the cosine squared of x, we're going to replace it with that. Okay, that's a general rule of thumb. If you have an even power, you generally are going to think about using those half angle identities. So let's write what we have now. So that's going to be the integral. This is now going to be, for the sine, you're going to have 1 minus cosine 2x over 2. The whole thing squared. And then the cosine, you're going to have 1 plus cosine 2x over 2 like that times dx. Okay, like that. All right, now the thing is, remember, you can integrate 1 plus cosine of 2x. Okay, so we like seeing that when that happens. Okay, well, one of the things we need to do on this one probably is we need to multiply all this stuff out and just kind of see where it leads us. Okay, so I'm going to do that. First of all, I'm just going to square this one in my head. Okay, if you have trouble with that, write it out twice and FOIL it. So 2 squared is 4. If you square that 1 minus cosine 2x, you would have 1 minus twice cosine 2x. Need to leave myself a little bit more room here. Okay, like that. And then plus cosine squared of 2x, like that. So that's what you're going to get when you get that squared then. And then I'm going to just bring this down. So I have 1 plus cosine 2x over 2 times dx, like that. Okay? So I'm going to kind of run through and get all that put together. So one of the things I'm going to do on this one now is I've got an 8. 4 times 2 is 8, so we might as well go ahead and take that out of the integral like that. And then what we can do is we probably want to just go through and kind of multiply the whole thing out and see what happens with this thing then. All right, so what I'm going to end up doing from here is we're just going to multiply this whole thing out right here. All right, because what we need to get everything multiplied out and just see if we can individually integrate things. Okay, so I'm going to kind of do this at the side of the paper over here. So I've got 1 minus 2 cosine 2x. And when you're doing these big messy problems like that, sometimes it's good to just go to the side of your paper, do a little scratch work, and then go back to where you are in the main work of your problem. So that's what I like to do a lot of times. So I'm going to go ahead and multiply that out and see where it takes us then. Okay, so I'm just going to do 1 times 1 is 1, and then 1 times cosine of 2x is cosine of 2x. Just going to do a distributive property. Then I'm going to do negative cosine 2x times 1. So that's minus cosine 2x. Then I'm going to do this. You've got to be careful here. I'm going to do that minus like that. So that's minus 2 cosine squared of 2x. Okay, like that. Then I've got to do cosine squared. Let me move this just a tad bit here. So I've got cosine squared of 2x times 1. And then finally, I've got cosine squared 2x times cosine is going to be plus cosine to the third of 2x like that. Okay, you guys get the gist of what I'm doing? Algebra, right? Okay. Now let's see if I got any like terms on this. Do I have any like terms? It looks like I have a couple of things here. So it looks like when I do this, I've got 1. These are like terms. Okay, so that's going to be minus cosine 2x. Okay, those go together. These right here go together. So that's minus 2 plus 1, so that is minus cosine squared of 2x. And then that last one is cosine cubed of 2x like that. Okay, now let me just pause there for a minute and see if we got any questions and kind of show you what my thought process is on this now. Okay? Now you got to be kind of careful with this. You know how to integrate that, obviously, right? You know how to integrate that, right?
Is that supposed to be squared cosine to its?
This right here?
Yeah.
No, because I put those together. That's not a square. Maybe you're looking at that as a square. I didn't write that very good. That's a 2x. Okay, like that. All right, do you know how to integrate this?
Yeah, I used that.
If you use that identity again, right? Okay, so you'd have to change that to this. Then you would know how to integrate it. Now you got a third power. Okay, what do you have to do with an odd power? You split it into the even and the one left over. Okay, so we're going to keep rolling with this. We're good there. We're good there. We can get good there. I'm just going to keep going with it, okay? Because we got to rewrite this thing in a certain form, so you have to kind of manage this carefully, all right? So watch carefully. All right, I'm going to bring these first two things down. I know how to integrate. We're cool. Now, this thing is a double angle or half angle identity, so we're going to replace this with this identity up here. Okay, so I'm going to rewrite that as, that one I'm going to rewrite, and you want to have a parenthesis around that. 1 plus cosine. Now, be careful about this now, okay? If you're going to use this identity, you're doubling that 2x, so what are you going to have? 4x, okay? So you got to have 1 plus 4x all over 2 like that. Now you got something you can integrate when you get to that point, okay? All right, now we're going to do this stuff here. Now with this thing, we're going to split this off into cosine squared of 2x times cosine x. That's the general strategy if you have an odd power, is break it off into an even so you can use that identity, okay? So we're getting closer. Let's just keep rolling with it. Kind of keep writing and bringing things down. Okay, I'm going to just distribute this through, and that's going to give minus 1/2 cosine of 4x, like that. So I'm just distributing the negative. Okay, what I'm going to do on this again is I'm going to use this identity again. So this thing right here is again a half angle identity. So you're going to go up here and do 1 plus cosine, double that angle over 2. So that is, again, is going to give me 1 plus cosine of 4x all over 2, like that. Okay, and then right here what I have is I have a cosine of 2x. So what I have to do on that is I have to use that identity again when I do that then. Okay, so I'm getting closer. I'm still not quite there. So I'm going to replace that right there, and then if I've got the cosine of 2x, I'm just going to bring that down kind of like that then. Okay, you guys with me? Okay. Now, what I want to kind of do here is I'm going to clean this up, and I'm going to go back and kind of see where we are with the integral. I'm going to write one more step on this. So that's 1 minus cosine 2x. Actually, one thing I do see we can do here is these are like terms, so we might as well put them together. Okay, 1 minus a half is a half. So that's 1/2 minus cosine 2x minus 1/2 cosine 4x, like this. Now this thing right here, I'm going to write this as just kind of write this the way it is, maybe bringing that 1/2 out, so we'd have 1/2, and then what I'd have here is 1 plus cosine 4x times cosine of 2x, kind of like that. Okay, so that's kind of where that would lead me when I get to this point then. Okay, now let's see, when I do this, there's one thing that I want to kind of show you on here, because let's kind of look at where we are. I think I've kind of gotten off track with one thing here. So what I'm kind of looking at this is you can integrate that, right? You can integrate that. You can integrate that. Here's the question right here is, can we integrate this? Well, if I go back in here, I see something that I shouldn't have done, okay? And that happens a lot of times when you're working out an integral. I'm kind of stuck with integrating that. But if I go back here, if I would have just left that the way it was, I could use a Pythagorean identity on that, okay? I could change that maybe to 1 minus sine squared. Then I could maybe do a U-substitution. So what I'm going to do is we're going to back up, and let's just kind of forget about this. And I didn't see it. I see it now, and that's what happens to you sometimes. You get to a point you're stuck because that's not going to integrate. But if you go back here, now you're kind of down to a point where you can do U-substitution if you change that to 1 minus sine squared 2x. Because you like the sine and cosine, right?
Can we multiply the cosine 2x into the 1 and...
Now you could, now see this one right here.
The last part we were in.
What's that?
The last part in parentheses, in brackets. Can we multiply the cosine 2x into 1 and the cosine 4x?
Oh, you could, it just wouldn't get you anywhere. You would end up with something that you wouldn't be able to integrate very well. Now if you did that, cosine of 2x, you can integrate that, but then you would have this product of those two things right there, which is something you wouldn't be able to integrate.
Okay.
Okay, that's why. So you're going to get stuck sometimes when you're at an integral, and you got to kind of back up and change things. So let me show you kind of what I saw on this. So what I'm going to have you do is we're going to adjust just one little thing here. Okay, so what we're going to do here is we're going to go through and we're going to change this thing right here, we're going to change that to 1 minus sine squared of 2x, and then leave that cosine of 2x alone like that. Okay, so I'm just going to write this now like this. Okay, now let me kind of talk through what I'm seeing, okay, because you need to see the same thing I'm seeing, okay? All right, you know how to integrate that, right? You know how to integrate that. You know how to integrate that. And you do know how to integrate that. That's a U-substitution. If you let U be sine of 2x, then the derivative is what's left over, right? So that's a nice U-substitution integral. So now we're ready to integrate. So all that work right there with trig, you're using identities to rearrange things so that you can integrate it. Okay, you guys with me? Okay. All right, so now we are going to integrate it. All right. And we're going to have to kind of do a U substitution at the side. So I'm going to go back to my problem now, okay? So what we've done, we took that 1/8 out, and so you got to keep track of stuff on here. Then I'm just going to plug in 1/2 minus cosine of 2x minus 1/2 cosine of 4x, and then plus 1 minus sine squared of 2x times cosine of 2x like that. Okay, and there's my little dx. I'll sneak my dx in there like that. Okay. All right, so now what we're ready to do is kind of wrap this thing up. So what I'm going to do on here is we're going to go ahead and just do the integration, okay, kind of bring things down very carefully. That's a 1/8 there, okay. The integral of 1/2 is 1/2 x, so we got that. Okay, what's the integral of cosine 2x in your head? 1 over 2 sine 2x, okay, that's that rule. 1 over a cosine, no, not cosine, sine of 2x, okay, like that. Okay, so we got that now. Okay, now we bring this down, minus 1/2. What's the integral of cosine of 4x? 1 over 4 sine of 4x like that. Okay, so we're doing pretty good. Now what I'm going to go ahead and do is I'm going to break this thing off, and we're going to do that integral just at the side of our paper. Okay, kind of go off and do some scratch work and keep track of things. So we're going to do the integral of 1 minus sine squared 2x cosine 2x dx like that. Okay, so you kind of keep track of stuff. These problems are a mess, so you have to have a strategy to keep track of everything. Go off to the side and do scratch work and keep your main work together. Okay, this is a U-substitution integral, so we're just going to let u be equal to just the sine of 2x. You only want that. And then du is going to be cosine 2x dx, but then you also got to be careful with that, and by chain rule, what do you have? Cosine 2x and then what? Times 2. So you got to be careful about that. Okay, you don't want to make one little mistake. Now if you divide both sides by 1/2, you would get 1/2 du equals cosine of x dx like that. Okay, now we already did that same integral a little earlier in class, so we're ready to do that. Okay, all right. So when we do that, see, this thing right here is going to be the u. This thing, the cosine 2x dx, is going to be a 1/2 du, like that. Okay? So now when we put this together, it looks like we're going to have the integral of 1 minus u squared. Okay, because u is just the sine of 2x. And then this is going to be 1/2 du, so I'll put the 1/2 there and the du there. Okay? All right, everybody with me on that? Okay, let's see what we have. We have 1/2. The integral of 1 is u. The integral of u to the second is u to the third over 3. And then we're going to plug everything in. Then we'll go back in our problem, and we'll be ready to clean up and finally get our answer. Okay? All right, everybody good? Okay, so let's see. What we have then is just plug back in the u now. So u is sine of 2x. So it looks like what I'm going to have is 1/2 of sine of 2x minus sine to the third of 2x all over 3 like that. All right, now I'm ready to just kind of go back to my integral and finally put this whole thing together. Okay. So I'm going to go ahead and like distribute the 1/2 through there, then I'm going to put this over here. So I'm going to have like plus 1/2 sine of 2x minus 1/6 of sine cubed 2x like that. Okay, and then that whole thing gets multiplied by an 8. God, I hope I hadn't made a mistake. These things are so easy to make one little slip up on. I think I'm okay though. Okay, so we got our integral. Now let's kind of take a look at what we have here. To me, the more steps you write, the better off. You can do this in your head, but I'm going to write this as 1/2 x, just clean it up a little bit, 1/2 sine 2x. That becomes 1/8 sine of 4x. And then this part right here is, just leave that alone, that's plus 1/2 sine of 2x minus 1/6 sine cubed 2x like that. And then we'd have the plus c there. So let's see. I do see one thing happening. Look inside of your brackets. What do you see, if anything? Yeah, sine 2x is cancel, so we can get rid of that. Okay. Then we multiply everything out, and then I hope we're done, and I hope I have the right answer. I'll check my notes. I think we're good. So we have 1 over 16x minus 1 over 64 sine of 4x, like that, and then minus 1 over 48 sine cubed of 2x, and then plus c. All right, so that's the answer. Wow, what do you think? Wasn't that fun? Okay.
There's a lot of partial credit on this.
Oh, yeah. Yeah, I mean, it's real easy to slip up. I mean, you just have to be very careful when you do that. So, but one strategy when you're doing problems that take like 20 steps like this, you got to kind of keep the main flow of the problem together and do some scratch work at the side, you know, so that you don't get lost in there. Now you can take the derivative and check your answer if you'd like. Usually students say, no way, I'm going there. Okay. All right. So you get into work. Now the key thing is just kind of take your time. And the key on so much of this stuff is whether you have an even or odd power. And these identities is what you got to do. These things get quite messy, like I told you. Okay, so let's see. This one is not as bad. This one I wanted to just kind of take something with a negative exponent in it. And that's not an inverse. That's a cosine negative 2x like this. And there's several approaches you could take on this. What we're going to generally look at is kind of what we have now is we have an odd power and we have an even power. The previous problem I did, we had two even powers. So you got what the powers are tells you the strategy you're going to use. So one thing you want to get clear in your mind is when you have an odd power, what do you generally do? Split it into the even and the one left over. You got to get that in your head. Okay? So that's kind of the general strategy we're going to use. So to start this problem, we're going to do that. We're going to break off that sine of x into sine squared x times sine of x, and then we're just going to leave the cosine alone like that. That's an even power. It's a negative exponent, but it's an even power. Okay? One thing that I see on this problem too is I kind of like having a sine and cosine in there. So what we generally are going to do on this, you got two choices. Okay? One choice would be with this thing, you could try the half angle identity. The other thing you could do is you could think about, you know, this identity and just see where it leads us. So we know that we have sine squared x plus cosine squared x equals 1. So what I'm going to do on this one is work with that identity. Okay? So I'm going to have you replace this with 1 minus cosine squared x. So I just substitute that in like that. Then I have a sine x right here. Then I have a cosine negative 2x dx like that. Okay, so I'm just doing a trig identity. Now, the next thing I would think about when I look at this problem, this is kind of what I was seeing, and it just takes practice to see stuff like that. If you multiply this out right here, what is that? It's going to be 1, isn't it? Because isn't that really just cosine z to the 0 power? That's kind of nice, okay? So we're going to just multiply it out and see where that takes us. That's kind of what I'm seeing in the problem is, let's multiply it out and see what we get. Let's do a distributive property, okay? So I'm going to take this whole thing and multiply it through like this. So I'm going to multiply that. That's going to give sine x times cosine negative 2x like that. Okay, then we're going to distribute this way. So that's minus sine x cosine negative 2x times cosine squared x dx like that. Okay, so sometimes you just run with an idea and see where it takes you, right? So let's see. The next thing I'm going to look at here is this thing right here goes to 1 because that's really cosine 0x, right? Anything to the 0 power is 1. So it looks like what we'd have is we'd be left with sine x cosine negative 2x minus sine x dx like that. And then we'll kind of pause there and kind of see what we can do on this then. Okay? All right. So let's kind of think about what we got here. All right. Does anybody have a question about the simplification? Has everybody got that okay? Let's do one identity. All right. Do you know how to integrate the sine? Of course. Okay. So that's cool. Let's think about, do you know how to integrate that? Remember, if you have an integral of the sine and cosine, you'd like that. So any suggestions on that integral? You could actually bring out the bottom and maybe do U-substitution. You like having a sine and cosine. So let's try that and see where that leads us. I think we're going to have to do a U-substitution on part of this. So let's write this next step kind of like this then. So let's write this as integral of sine x over cosine squared x. Okay, I'm just bringing that down to the denominator like that. Okay, so I got cosine squared x, and then I got minus sine x times dx like that. Okay, so let's just split this into two integrals. One of them, of course, we can do in our head. The other one is probably U-substitution. So let's look at the integral sine x over cosine squared x dx. And then let's look at the integral of sine x dx like that. Okay? So I'm going to kind of go over at the side of my paper, and we're going to work this one out with just a U-substitution. Okay? So I'm going to do a little scratch work on this. Okay, so if I'm doing the integral of sine x over cosine squared x dx, okay, what would be a good thing to let u be equal to in this problem? Cosine. Okay? And the reason is because the derivative of the cosine is negative sine, so that'll work well. So let's let u, not the cosine squared, you don't want to do that because it won't work. You want to just have it equal to the cosine x only like that. Okay? And then you would like for du to be sine of x or something close. So du is going to give negative sine x times dx like that. So you can just divide both sides by a negative and rewrite that as negative du is sine x dx. So that means this is going to be u, and then this numerator is going to be negative du like that. Okay, so that's a pretty straightforward U substitution that we should be able to do. Okay, everybody okay? Okay, let's see kind of what we have here. So it looks like we have sine x dx is negative du. I'll just put the negative in front of the integral. And then that will be u squared. Is that an integral you know how to do? Absolutely. Okay, that one would be negative integral u to the negative 2 du. And that's a power rule integral is all that is. So that value of that integral would be negative u. Again, what you're doing is negative 2 plus 1 is negative 1. Then divide by that plus c. Okay, like that. So that the two negatives cross out, just leaving you u to the negative 1. And then if we go back in and substitute now, u was cosine. So that means what we would end up getting is we would get cosine negative 1 x like that. Okay, and then we'll kind of go back in and finish our integral and think about what we can do with that then. Okay? All right, any questions so far about anything? Okay, let's write what we got now. If we go here, this integral we just did, and we got cosine negative 1x. Now, that's not an inverse. That's a negative 1 power. And then, of course, what's the integral of the sine? Negative cosine. Okay, that's a rule you know. So that's negative cosine x plus c. So here's what I would do is really, you could write this as 1 over cosine x. That's not an inverse. That's a negative 1 power. Then you could write this as plus cosine x plus c. What's a real simple thing you could do on this problem? Secant, exactly. Remember, the secant is 1 over cosine. So you have that identity, secant x is 1 over cosine x. So I'm going to write my final answer as secant x plus cosine x plus c. Problem done. Yep.
Is there any way to differentiate between like a trig identity to a negative power and the inverse identity?
Not really. I mean, it's just
context.
Yeah, it's more the context. So I mean that you got to be careful about that. I knew that because I was doing the power rule over here, that was a -1 power. So yeah, it's more the context. It's just the notation is going to look exactly the same on a -1 power.
Will there ever be a problem where it's like sine cubed of x times cosine of -1 of x? Or
Not in this section. We're not dealing with inverse trig functions at all yet. We get to that a little bit later, but in the context of these problems, no, there won't be an inverse in there.
But it's generally avoided to avoid that confusion.
Well, it's just that the integral has to be done a totally different way. When you're doing inverse trig functions and integrating, it's a totally different strategy. Okay, so how did that one look? Okay, kind of fun. I just think it's fun. I just love doing integrals. That's what I do on Saturday night. I just do integrals. That keeps me out of trouble. I don't go to a bar. I just work integrals out. Okay, so on this next page, what I'm going to show you is, now this thing right here, I took this out of the book. This is kind of the general strategies that we kind of talked about. We just focus on sine and cosine is to start with. It just kind of tells you if you have an odd exponent, you split it off to the even and so forth. So you can refer to that as you need to. And then sometimes you have to experiment a little bit. So those are kind of the ideas. The next thing we have is reduction formulas. So in reality, you know, you're a Calculus 2 student, so you're learning integration techniques, okay? All of these problems, if you have like a sine, cosine, tangent, or secant to any integer power, a positive integer power, we do have what we call a reduction formula, which I'm going to show you how to use one of those. A lot of times in higher math, you're more likely to just on problems like this, just use a reduction formula instead of using all of those techniques I showed you. Because like if you had something like a sine to the 100th power, okay, and you were trying to integrate that thing, oh my God, okay, if you had to do that by hand, using the techniques I do there, that'd be ridiculous. So some mathematicians have come up with reduction formulas. So I'm going to take you through those. You don't have to memorize the reduction formulas either. You want to refer to these things as you need them, okay? So I'm going to do, I think on this one, we're going to use the tangent reduction formula on this. And generally, you know, in your homework, it'll tell you use reduction formula, okay? Now, so what we're going to do with this one, you just follow the formula. So what we do with this tangent is we do this. Whenever we have a tangent of n to the x, you follow this formula exactly. So let me show you how you would do this then. And you have to be able to interpret that formula correctly. Okay? Well, in my problem, n is 4. Everywhere I see an n, I'm going to just plug in a 4. Okay, like that. I'll plug it in and see where that leads me. So what I'm going to have is I'm going to have the tangent 4 minus 1x over 4 minus 1. You can do this in your head, but I think it's helpful to just kind of write it down. This would be tangent of 4 minus 2 x dx like that. So I'm just looking at the formula. Again, I don't expect you to memorize the formula. You can if you want to. I don't have them memorized. They have similar patterns to it. So just plug it in and now we'll see where we're at. So the next thing we have is tangent third of x over 3 minus the integral of tangent squared x dx like that then. Okay, so that's kind of the idea of how you could do that. All right. Well, let's see. I'm going to write this as 1/3. You don't have to do that, but I just like writing that like that. Okay. Now what we got to think of next here is kind of what you're going to do with a tangent squared integral. Okay, so we got to think about how we would do that. Okay. All right, let's think about that a little bit. I'm just going to go over to the side and think about tangent squared like that. Okay, well, there's an identity, right? Okay, the identity that comes in real handy a lot of times is this one. Okay, you basically have 1 plus secant squared x is equal to tangent squared x. That's a useful identity that might help us. Okay, I don't have a formula for the integral of the tangent squared, but I can use this identity to do this. So what I'm going to do is I'm going to rewrite this like this. Okay, I'm just going to change this like this. Hold on, I think I got that identity wrong there.
1 minus secant squared?
No, that's okay. So I've got, see, this is the one I tell students all the time, I always forget. I remember sine plus cosine squared equals 1. If I divide by cosine, I get, yeah, okay, tangent squared x plus 1 equals secant squared x, like that, okay? I always have to derive that. I don't know why, as long as I've been teaching, I never can remember that identity. All right, so we have that. All right, so here's what you're going to do. You're going to write this as tangent squared x equals secant squared x minus 1, like that. Okay, just use that. So when I come down here to my problem, what I'm going to do is I'm going to replace this tangent squared with secant squared minus 1. Do you know why I'm doing that? Do you know what the integral of secant squared is? Tangent, that's why. Do you know what the integral of 1 is? X, that's why. Okay, so you got to use identities. When you're doing trig integrals, you use identities all the time. So you want to replace that with secant squared x minus 1 dx, like that. Now we're ready to integrate, so you can do the rest of this in your head. So this just comes down. So that's 1/3 tangent cubed x. Okay, this integral right here is the tangent of x. Okay, like that. Okay, because the derivative of a tangent is a secant squared. And then the integral of 1 is x plus c. Okay, so the final answer on the problem, the best way to write the final answer would just be like this. We'd say 1/3 tangent to the third x minus tangent x plus x plus c, and then that should be the solution to your problem. Okay? And again, what I spotted on that is tangent squared. If I use a secant squared, then I know the integral, because you know the integral secant squared is tangent. Does that make sense? Okay? All right, now see, a reduction formula is not too hard. I mean, putting it in the formula is pretty easy, and then generally you're going to be left over with one integral. All the reduction formula does, it makes the powers go down. And the further they go down, the better off you are. Okay? All right, so that's how that would go. I think the other thing I wanted to do on this problem is I wanted to redo this same problem just in a different method. And then we'll kind of go through and start looking at a few other integral formulas here. So I'm going to just redo this. Now you can do the reduction formula on that, but if you weren't doing a reduction formula, this would be kind of the idea of how I would reason this out. Okay, well, I'm going to use that identity. Okay, so there's the identity. Okay, so what we're going to do is we're just going to change the tangent to what it's equal to, just kind of like what we were doing in the last problem. So I'm going to have the integral. Again, write this like this, and you can do this all in one step in your head if you want to. I don't care. I'm going to write this as tangent squared x to the second dx, like that. Okay, so we're squaring something to the second power. Then what I'm going to do is I'm going to replace that, just like I did in the last problem, with secant squared x minus 1, and then squared like that. Okay, so I'm just kind of replacing an equal with an equal like that then. Okay? All right, now what I would have with that then is, let's see if that would get me anywhere. I think there's something I need to do on this now that I think of it. Sometimes I try something and then I realize I'm not going right, which is okay. I want you to see that. That's normal, okay? what I'm going to do with this one is, if I multiplied that out, I would end up with a secant to the 4th power. We don't know how to deal with that. So what I'm going to do is I'm going to write this way instead. Okay? Just this way. It's a little bit better to write it like this. Now I see where it's going. Sometimes I don't see that immediately. So let's write that as tangent squared x times tangent squared x dx. Okay? Now there's a reason why I'm doing that. We're trying to see if we can get a U substitution out of this. And what I'm going to do is I'm going to keep this one, just leave that one alone. This one is the one I'm going to replace with that identity. Then I'll kind of show you what my thought process is. So let's leave that as a tangent squared x. Let's change that tangent to secant squared x minus 1 dx like that. Okay, now let's just kind of pause here and let's think about this for a minute. Okay? And kind of think about what we're dealing with here. So, all right, let's just think U substitution. Okay, do you see anything? Do you see what I see? What did you let U be? Tangent, right. If we just let U be tangent, what's the derivative of the tangent? Secant squared. So we might be able to get somewhere by doing that possibly, okay? That's kind of what I'm reasoning through as I look at the problem. So we might be able to do something kind of like that then. So let's try that approach. So let's let U be the tangent of x, okay, just the tangent, okay? And then what we'll have on that is we'll have du like that. Oh, okay, I got to split this off though. I got to think about this before I do this. I'm getting ahead of myself. So let's actually write this as tangent squared x secant squared x minus the integral of tangent squared x like that. So I'm going to split it off into 2 integrals and do that. It's because if you do du, you would have secant squared. You wouldn't have secant squared minus 1. So I'm going to have you just kind of multiply that out like this then. Okay, so now I'm going to go through and I'm going to do the U substitution on this then when I do this. Okay. All right, so now I'm ready to do U substitution on this one, and then this one I'm going to use a secant on like this. So now I think I'm in business. Okay, so we're going to do a U substitution on this one. Okay, so I'm going to kind of go at the side of my paper and just focus just on the integral of tangent squared x secant squared x dx like that. Okay, now what I'm going to do is we're going to let U be the tangent of x. Okay, and then du is secant squared of x like that. Now see, that's the reason why I split that up into 2 integrals, because when I was doing this, I was thinking, okay, a du would be, we would want it to be just a secant, not secant squared x minus 1. So that's the idea. Okay, so when I do that now, I've got a real simple integral. So what I'm going to have is this thing right here is the u, and then this thing right here is the du. So you would just have u squared du like that, okay? And then that's a real easy integral to do. So that would be u to the 3rd over 3. And then u is the tangent. So now if I plug that back in, what I would have is this would just be 1/3 of tangent to the 3rd x like that. So that's what the value of that integral would be. Okay? So what I've kind of done there, see, is I've split this off, and I saw this as a U substitution right here. Okay? Does that make sense? Okay? It's because I see that when I see a tangent, I like seeing the secant squared. Okay? That's the idea. And then we'll have to focus on how to do this integral right here. Then we'll be almost done here. We'll see if we get the same answer. Okay, so the way this one works is like this. We got this one done. This one is 1/3 tangent cubed of x. Okay, now we've done this tangent before. The idea is you want to work with this, with that identity again. So when I do this second integral, I want to use an identity. And we've done this, it seems like, a couple of times. So the tangent squared, I'm going to change that to secant squared x minus 1 dx. Why did I do that, by the way? Because you know the integral of the secant squared, right? And you know the integral of 1. That's why I did it. So now I'm ready to just finish that integral up. So I'd have 1/3 tangent cubed of x. And be careful with that minus. So the integral of secant squared is tangent x. And then the integral of 1 is x plus c. And then if I finish this up, I'm going to have 1/3 tangent cubed x minus tangent x plus x plus c, like that. And there's your answer to your problem. I hope that's the same as I got the last time. Is that the same as what I got on the last problem? I guess it is. Okay. So to me, the reduction formula is easier on that problem. What do you think? Now, it saves a little bit of time. So in general, reduction formulas do come in kind of handy. They really do. Okay. So I do want you to know something about the reduction formulas. Okay. All right. Let's do kind of go over these rules here, and let's work with this just a little bit, then we'll take our break here in a little bit. So what I want to kind of do on this, these are nice to know. So I would recommend that you kind of work on learning these things. A lot of these things can be derived. I pretty well can I can derive the first two in my head. That's worth showing you. Okay. So actually, the integral of the cotangent is easy to reason out in your head. It's the logarithm of sine x. Okay, now just think about that. What would be the derivative of the ln of sine x? It'd be 1 over sine x times the derivative of the sine x, which is what?
Negative cosine.
There you go. Okay? Or derivative of sine is cosine, right? Yeah, just cosine. So that would match a cotangent. So see, that would be 1 over sine times cosine. And what's cosine over sine? Cotangent, okay? This one is a little harder to figure out, but if you do this, the derivative of this would be 1 over cosine times negative sine. What's sine over cosine? Tangent, but you have that extra negative to cancel out that negative. So a lot of times you can reason that out. A tangent and a cotangent has a natural logarithm. These are a little harder to figure out, but they have kind of a similar structure to them. Okay, so what I'm going to do is just kind of show you how to derive a couple of these. When you see an integral of a tangent, you want to either know this formula or you want to be able to derive it real fast. So I'm going to go ahead and derive the tangent formula for you and just kind of show you how to do this. And I think we've done this before this semester. This has shown up enough that we've learned how to do this integral, I think. Okay, how do you suggest I start? Identity. There you go, sine over cosine, all right? So let's rewrite this as sine x over cosine x dx. See, we like it when we have a sine and cosine the same integral. Now this looks like a beautiful U-substitution to me. Okay, tell me what I should let U be equal to. Cosine. The reason is because du will match close to what we're looking for. Okay, so if we do du, we want to end up with the sine of x dx or something close. Okay, so that means that du is going to be negative sine x, like that. So if I divide or multiply both sides by a negative, I'm going to get that. Okay, so that means that this part's going to be negative du like that. All right, so what we're going to end up having then is we're going to end up having the integral of u in the bottom and then negative du like that. Okay, what's the value of that integral? Negative ln of u, right? Okay, that's an ln logarithm, so you're going to end up with negative ln of u plus c. Now you can go back and plug back in the u. The u is the cosine. So what you would have here is you would have negative ln cosine x plus c. Okay, so that's what that piece right there is. I've just proved that part right there. Now what we need to do next is we need to kind of show this part right here. That's another way of writing the same thing. So let's see if we can reason out how this goes. Negative ln cosine x plus c. All right, any suggestions? I have a negative in front of a logarithm. That kind of makes me think of something. What do you think? Bring it up. Exactly. If you have a number in front of a logarithm, you can bring it up. So what you actually could do on this then is, since that's a -1, you could bring it up. So you'd end up having ln of cosine of x to the -1 power plus c, like that. Okay, now that's not an inverse. We kind of got into that. Well, now what you could do is you could write that as 1 over cosine. Okay, how come? Because if you have a -1 power, how do you make it a positive exponent? You bring it down. So what I was doing really is thinking of that as just bringing that exponent down like that. And then, of course, what's 1 over cosine? Secant. Does that make sense? Okay, don't confuse that -1 with inverse. That is a -1 power. So that's how you would prove that formula. So deriving that formula is easy. And you want to know how to derive as many things as you can, so you don't have to memorize a million things. Okay, you see what I mean? Okay, that's a real easy one to derive. Okay, let's do one more here, and then we'll take a short break here. So let's derive this one. I would recommend that, that you might think about outside of class, trying to see if you can derive those. So what I'm going to do with this one is a very similar derivation. Okay, so what we're going to do is we're going to do U-substitution. We're going to change the cotangent to cosine x over sine x dx, like that. So use the ratio identity. Then we're going to do U-substitution. So we're going to let u be the sine of x. So that'll be the denominator. And then we're going to let du would now be cosine x dx. And then we got a super easy integral on this one to do. Okay, so what that's going to leave me with here is the integral of du over u, which again is what? Natural logarithm of u. Okay, so that's going to be ln u plus c. Okay, now we're done. Okay, because you basically just have replaced that like that, and then you got the answer. So that one is ln of sine x plus c. Okay, so there is benefit to remembering that formula for an integral of a cotangent or a tangent, or just being able to derive it pretty quickly. Okay, because you are going to forget them. Okay, all right, how's that look to everybody? Well, that's a lot easier than some of the integrals I've done today. Okay, all right, are we good? Okay, well, let's go ahead and take a 10-minute break and come back at 20 after, and then we'll push on with this a little bit.